I'm basically following the book. Okay, so when I put 1.2, it's basically 1.2 in the book. And as I said, some of you who don't want to take notes, that's fine. I'll post all these things. Okay. Okay, so the thing about mechanical engineering design is that it's no longer compartmentalization. It's not like this topic is by itself. It draws inspiration from many other topics which you'll be studying in this degree, right? You have mechanics of so design is interdisciplinary. And then we'll see that we will utilize some things we learned in previous courses, like mechanics of solids. This is a prereq for this course. Manufacturing. Fluids, including thermodynamics. Electrical engineering, that's because when you design things, you typically have a power source and there are electrons moving, right? And so you can't really disassociate with that. And then modern day design cannot stand by itself because you need a computer, and that computer needs to be programmed and told commands on what to do. So so it really encompasses pretty much everything you'll be doing here. All those things are important. When you design something, it's not only the stress, but also about what program will run on it, how will it function, can you manufacture it in bulk, can you market it, can you sell it, and so on. Economics, everything is important. So people like to look at design. So now when you see design, you think of design of some product or some part, right? So when you have a design, you think of a flow chart which takes you from the start where there's a need all the way to the finishing or selling that product. So this is a way the book talks about the phases in design. So phases of okay, and so this is pretty much self-explanatory, right? You first have a need. Once you have a need, then you need to define what the problem is. So if you want to go from point A to point B, you need something to transport you. And then the question is, so that's the need, right? To go from point A to point B. And how do you define the problem, where the problem is to create a device which will take you from A to B. And then when you have that definition of the problem, you come up with a solution. It could be a car, it could be a bicycle, it could be a plane, or whatever you want. And then you basically go through the process of design, which is basically the next 3 steps, which is you synthesize based on your problem, you analyze, write equations, see what the forces are, compute quantities of interest, you evaluate that. Typically there'll be metrics on whether if you have like a cost target, or you have a speed target, in this case of transportation example, then you have to evaluate those solutions against that. And once you do that, you finally can go and present it and of course make the product. Now, design doesn't tend to be linear in the sense you think that those are the stages, and once you do those, you're done. Typically, you will have the stage where you create something, you evaluate it, and only when you test it, you realize flaws in it, and then you need to redo the whole process. Sometimes you realize the flaws when you do the analysis, and then you need to go back to the problem. So it's very non-linear, and you'll get a taste of this when you do the course on senior design, where we'll actually go through this process once and you'll create something. You'll not really do it you will not see so much non-linearity when you do it in senior design. It's very structured. Okay. So by the way, that's taken from the book. Okay. Okay, so let's talk a little bit about the design tools. And some of these tools you've learned, and some of these tools you'll hopefully learn in courses here. Okay. So computer-aided design. People like to abbreviate that as CAD. Okay, that's like the main thing here, right? If you want to show a design, you can draw it on paper, which is the first step. But if you want to communicate that with another engineer, you want to draw it on a software which allows you to put dimensions and shows you the mating of assemblies, puts tolerances, and so on. So this basically gives you 3D views, dimensions. Sometimes mass, inertia are important, especially for things which are dynamic. If something is very heavy, then it's very difficult to transport it, or you'll have to size the motors. Center of mass. And the tools which are typically used here are Inventor, SolidWorks, and we have licenses for this. So if you have taken 250, you probably know these tools. There's a tool called Finite Element Analysis. It's often abbreviated as FEM. Okay, we have an elective in our curriculum on finite element analysis. This basically tells you stress, strains, thermoelectric stress, strain, so on, when the geometries are pretty complex. So simple structures like beams we'll be talking in the class, you can write the equations by hand. But once geometry becomes complicated, there's contact, it's just hard to do these calculations by hand. And we rely on a tool called finite element analysis to do that. So this basically helps you to do stress, strain, deflections, vibrations, heat transfer. Okay, and the tool which is typically used in the curriculum here is called ANSYS. And I forget what that acronym is for, but you can search ansys.com and you have more information on ANSYS. So then the people who are interested in fluids, right? And fluids is important because some of the mechanical structures are subject to fluid forces. There's something called computational fluid dynamics. It's called CFD. Okay, this is basically concerned with fluid flow. The tool which is used is called Fluent. Now, we actually also have electives on CFD. So if you're interested in CFD, computational fluid dynamics, I'm pretty sure you can find something of interest. Okay, then we have dynamics, which is a course you must have taken in the past. Okay, this is concerned with forces, motion, okay, and also sometimes, you know, when you create mechanisms, so like for example, the piston in your car, the pistons, the slider crank chain assembly, which basically is the cylinder which basically has the gasoline. It's basically a mechanism, and when it spins, when it's moving, the connecting rod, the shaft is moving, is subjected to forces, and those forces are kind of important if you want to build the system and make it work reliably. So that is typically done using a software called Adams. And this goes slightly beyond what you've learned in dynamics, which is good for doing simple problems. Once the problems become bigger and big enough, and the interaction forces are more complicated, it's just not possible to do these calculations by using engineering dynamics. Though I must say that many of the calculations you can do by hand, get a ballpark figure, and if you want to get a exact number on how these forces interact and produce things of interest, then you want to go to Adams. And then there are generic tools. And these are sort of your data processing, data mining tools. Some people like to use Excel. There's Matlab, which is nice because it's kind of free for academic purposes. But if you go to the industry, you'll see that people don't use Matlab. And that's because it's not free. It's expensive to have Matlab in the industry. It's kind of cheap in the education. So people typically in industry will see using Python, which is an open source numerical package, just like Matlab. And then Maple is another one, which is used for symbolic stuff. What I mean by symbolic stuff is you want the equations or do some analysis where you have variables instead of numbers, then Maple is usually the choice. So what are the design courses here? Courses in ME. So we have ME 250, intro to engineering design and graphics, which you probably have taken. And I really like that course because it takes you just beyond design. It teaches about automation too, which I think is very important because almost everything you buy these days has a microcontroller inside it, either sensing environment around it or doing something useful with motors. There's ME 347, intro to computer aided design. There's ME 370, which is this course. And then the fourth one, and this is probably the culmination of your 4 years here, is the ME 396, 397. It's the senior design 1 and 2. So that's a sequence course. So senior design 1 is where you'll basically build something on a computer, and you'll have designs on paper. But senior design 2 is where you'll actually take that design and construct something which will be in the real world and not on paper, right?